Good afternoon, everyone. My name is Aliyu Kasimu, and this is the first session of our Hexagon, our Hexagon computer-aided engineering session, and we've done it. We've organized this event just for us to come and enjoy some, CAE demonstrations. Abdulhamid, sorry, can you stop sharing your screen? Let me do a brief introduction on Hexagon.
Okay, okay.
Yeah. Or maybe you don't have to. I'll just override you since I'm the.
Okay,
So can you all see my screen? Can you see my screen? Hello. Can someone confirm if you see my screen?
yes, I can see your screen.
Okay. So basically, I just want to introduce this. I don't know this. Okay, Hexagon. So Hexagon is this company. Or basically, I'm going to introduce what Hexagon CAE is and its role or its potential roles in our research works. So if you know MSc software, if you've heard of MSc Adams or MSc Nastran, if you've heard of MSc in relation to CAE software solutions, then that is what Hexagon is. So the name basically changed because Hexagon company bought MSc software solutions. So basically, this Hexagon CAE, the Hexagon CAE package allows you to do computer-aided engineering, including finite element analysis, which is the most popular CAE tool currently. And then there's computational fluid dynamics (CFD), and even multi-body dynamics through so many softwares that they have. Here there are so many softwares, including Adams autonomous mobility software suites, the FTI suites, where you can simulate the forming process for thin sheets. And then you have the multi-physics simulation software where you can do your multi-physics simulations. You have the Romax where you can do electromechanical simulation and design. You have Simofact, Digimat where you can do nonlinear multi-scale material and structural modeling platform. You have so many others. You have EZ5. With EZ5, you can simplify the process of doing graphical construction analysis of dynamic systems. We have the elements, the material center, which I've introduced some people to, and I'm glad that with Hexagon now I have so many people, multiple people, not very much, but a humble number of people who currently use the material center. They also use Adams software for their multi-body dynamics research, and then also Digimat for multi-scale material modeling. And this is very, very important for people who are doing materials research. And then so it offers you also the virtual test drive. You can test drive your systems, especially if you're doing automobile research. So the software I've gotten very close to is the Adams because my research area is basically multi-body dynamics. Even though it is it is related to train or railway train multi-body dynamics that Adams does not offer. But if you are doing any other simulation, for example, gearbox, transmission systems, the drive line, the powertrain, and any of these kind of multi-body dynamic systems that do not require a certain preset form of environment to thrive or to work, then you can easily use Adams. And why I'm sharing all this is for all of these softwares that I have mentioned, I can provide you with resources to learn them and to use them. directly from the company, because I'm the CAE Student Ambassador for Central South University. So we'll talk briefly on Adams, because it's basically what I use most, or what I've learned most. So basically, you can do, this is a transmission system. You can do analysis on transmission system. This is you can do analysis on the on roller rigs, analysis of suspension systems on roller rigs. You can do stress analysis. This is flexible body analysis in multi-body dynamics. You have the system, the piston, and etc. So you have, what you can do is basically, it allows you, this collaboration, this very important collaboration between the traditional FEA softwares and the ADAMS, which is the multi-body dynamics. So you can, for example, if you preset this motion in ADAMS, all the forces that interact or that come into play, you can export them to Abacus or ANSYS or any other finite element analysis to do proper force analysis, because it will give you all the forces that are present here, and their directions, their vector, the force vector, basically. So in Adams, using Adams, you can do controls and mechatronics. You can do flexible body integration. What I've just mentioned, you can do component durability analysis. To see the half-life, or the duration, the service life of any component. Also vibration. People who are into vibration can use Adams and to do many of these things. And then there's a more holistic arrangement that is also related to Adams. It's called the Adams car, where you can do basically any form of car simulation, dynamic simulation that you need to do. And then there's the machinery. You can also do noise analysis with Adams as a major contributor. So basically, this is what I want to show you guys. If anyone needs any help with these software solutions, I'll drop this link in the group. I have enormous amount of resources to support you on this, and I will be very glad to give you these resources. Please feel free to explore some of these softwares and see if you are interested. If you're interested, just get to me. I have all the resources directly from the Hexagon company to support you on this. So thank you very much. Our first presenter is Abdul Hamid, and I'll allow him to share his screen now. Abdulhamid, can you share your screen? Abdulhamid is going to talk about computer-aided design. No CAE, no computer-aided engineering, just computer-aided design. Please share your screen, Abdulhamid.
Can everyone see my screen?
Yes, we can see your screen.
Okay. So, good morning, everyone. My name is Abdul Hamid Abdul Karim. So I'm just going to be giving a brief overview about CAD, that's computer-aided design. I'm sure, well, I hope some of us, or all of us at least, have some understanding of CAD. Well, not even I'm sure. I'm very sure already that most people here are not new to CAD. So basically, as the name suggests, computer-aided design, is just software, used for production of productivity, design. Let's just say it is used for design improvement using computer. You can also use it for manufacturing and so on and so forth. So basically today I'm just going to be showing some examples of some CAD models that I did. I'm going to base these examples just to two software, that is Blender and then SolidWorks. So, but before I go into that, we have different type of CAD. We already know, CAD can be 2D, it could be 3D, but basically what I'm going to be showing here is going to be 3D CAD. That's what I'm going to be focused on. And there are also other software that you could use. You have Maya, you have 3D Xmax, you have Cinema 4D that you could also use in place of these two software that I'm using. But so basically, let me start with Blender. This right here, this interface, this software interface here is Blender. Now this computer aided design software, which is Blender, it's a very interesting software, to be honest. It's the software that you can use to do a variety of things. So one of the things you can do, I'll just be showing like some of the things you can do with Blender. If you look up here at this tab here, you see a variety of things. You can see modeling, sculpting, UV editing, texture paint, animation, rendering, composition, and then you see geometry node. So what this software allows is just like a complete package for you to do both. You can do your modeling here, be it hard body modeling or non-destructive modeling. What that basically means is uh, if you look at the software, if you have experience with the software like SolidWorks, the you notice it's more focused on engineering um, kind of designs. You cannot use SolidWorks, for example, now to comfortably model. Let's say if you're trying to model a terrain, it's going to be very challenging. I don't know if everyone can hear me. Uh, oh my God.
We can hear you. We can hear you. We can hear you.
Okay. Thank you. So it's going to be very challenging if you want to try and use a software like SolidWorks to model a terrain, for example, or model trees, 3D trees, for example. But you see, with a software like Blender, for example, now it's very good when it comes to illustrations. So you could do things starting from terrains, topographies, you could do animations and a whole lot of things. It's a software that is currently being used for even blockbuster movie productions as we speak currently. So it's a very interesting software. So if you come to modeling, basically what modeling allows you to do is it will allow you model just as the name says objects. So be it animate or inanimate objects. You can model, like from what you can see here, this is a local grinding machine that some of us may be conversant with. No. So you could model things like this, or you could model topographies, let's say landscapes, and you could also model things like characters. So I'll just try and see if I can open some. Okay, let's see. Let's sorry, just trying to show you. This is like a just a I don't know, water board. Let's say your water supply companies normally have their uh, what do you call it, control centers. So this is something showing that you have to forgive me. It's showing a wireframe. Okay? So with model things like this, everything here you see was modeled using Blender. You could do things like this also. You could do things, you could model things like characters. Let me see if I can also show you something like that. You could model environments. For example, let's say this is a boardroom. Now, when modeling, you could decide. The good thing about Blender is you can model to scale, or you could just model, just have a free range of modeling. It really is not too constrained to dimensions like software like SolidWorks that you have to put dimensions into consideration when modeling. I think with Blender, what you really focus on more is your scale to see that everything is scale is right relative to another object. So this chairs now, for example, I could decide to scale it upwards or downward without really considering how dimensionally accurate it is, as far as it is um, scale wise okay compared to the table and the rest. So basically, you can do that for modeling in Blender. You could also do sculpting. Now, sculpting you could do if you see there's a well, I don't know if any of you have seen these videos online now where you see you see 3D characters. If you are conversant with the metaverse, so you could do sculpting, you could do character sculpting there where you actually, make a 3D representation of a live character there. So, and then you have your UV editing. So that's, you can apply materials. If you look at this table, for example, they give the illusion of this is a wood. So what UV editing simply means is you can apply specific, materials and give them high details. So, and then you have animation also. I'm just going to show a brief illustration of this. So, for example, people who are interested in making cartoons, for example, or people who do movies productions. So you can also use Blender for animation. This is just a simple animation to serve as an illustration, where you could do something much more interesting than this with Blender. So this is just to show you some character trying to just animate them move close to each other. So you could also do things like this, and things as complicated as you having you could call it like an augmented animation where you have scenes. You can take a video, just like video editing. You take videos of real life scenes and then you bring it into the software, and you can actually integrate them with characters you model, basically CGI. That's you could do things like, if you watch movies, you see creatures and animals, things like that coming into the scene. You can do things like that also with Blender. And then you could also do strict video editing where you cut, you edit, you also what do you call it? You basically model a video that you've taken to whatever it is that you desire. Let's say if I take a video of myself now, for example, standing and walking, I could do the editing of the background, or editing of myself, maybe flying or doing some very, very fantastic things. So Blender is just a complete like workshop when it comes to anything that has to do with 3D. Basically, it also supports 2D, but um it is tilted towards 3D more. So it will just give you a room for you to start and do a complete production when it comes to let's say studio work. You can start from your modeling, sculpting, all the way to your video editing, all in Blender without having to export any of your files to another software. It also supports scripting also. It supports code in what do you call it? Python. That's the language it supports. So it supports game production also. You could also use Blender for game production. So basically, that's all there is about Blender. Just a brief uh, explanation on what Blender can do. So I'm also going to show another software now, which is SolidWorks. It's also a very, very interesting software. So while Blender, like I said, allows you to do things like modeling, sculpting, and some very, very interesting things. You see SolidWorks, basically it's more for the engineering guys. I'm going to be using a number of models to show what SolidWorks is actually all about. So in SolidWorks, we have it's also a computer aided design software, but unlike Blender, where you can do terrain modeling, and then you can do serious animation. You could do animation in SolidWorks also, but just it is limited to, there are a lot of constraints in the kind of animation you can do in SolidWorks. So this model I'm showing is it's called a noisemaker. It's supposed to be a prototype for I don't know, for it's a speaker. It's supposed to be a speaker shell, a speaker housing. So it's a prototype for it. I'm just going to, basically you have different components. This is just the assembly trying to show what it is all about. So, but first, before I go to this, let me try and just introduce you guys to. So SolidWorks has three major parts. So you have the parts modeling, which is your 3D representations, just of a single model, and then you have your assembly. That's where you bring in different parts and then try and assemble them, and then you have the 2D engineering drawing, which, like I said before, CAD can be 2D, 3D, or even 2.5D. So with SolidWorks now, you have you have two, or will I say you have two out of those three. You have 2D and 3D, but SolidWorks doesn't, to the best of my knowledge, support 2.5D. So if we go to part now, what part does is it allows you to just model the single, you could model a single part. Let's say I could just do something like, bear with me, I could do something like this in a part, for example. Now this could just serve as, it's just a simple model, but this is just a part model. I cannot, while in this particular interface, you cannot do assembly modeling here. You just model the parts like I've explained earlier, and then when you're done with all your part models, then you can now come to the assembly, where you start integrating those different parts you've modeled, into a system of some sort. This is another model, the complete system. Let me try and show that. Sorry for the, just takes time to load sometimes. When you have so many parts, it's very taxing on the computer if you have so many parts. So this particular model now has over 200 plus parts. So it takes a lot of toll on the system. So basically what you're looking at here now is it is a device. It's called a pasta maker. So this device is meant to actually cook, and it's meant to be like a vending machine of some sort, but in this case, just for pasta, that is noodles. So that's what this device you're looking at is here. Let me try and show the parts so that to make more sense. Please bear with me. I'm coming. Let me just have to suppress so many things. I don't know if everyone is still with me.
Yes, we're with you.
Yes.
Okay, so I'm trying to just this device, for example, show some of its components. So you see, if you can see my screen here now, so this is call it a full system. So this device is meant to be a pasta making machine. I could just explain briefly how the process works. So basically, you're meant to be able to load, your pasta doughs here, and then using the same principle vending machines use. This is meant to convey uh, what is it? This is meant to convey like your dough into this mixer here. This is a mixer here, and then after mixing it shapes also, and then you have the option of actually cooking. You can cook the pasta here and also fry, and at the same time serve. the principle it uses is for motion. It uses like the same principle that 3D printers use to move in, let's say, three axes. So that's what it uses basically. So this is just what you can do with SolidWorks assembly. Now, when you're done assembling for engineers, it really means nothing if no one can work with what you've done. That's where the third part of SolidWorks come in, which is the engineering paper. So this is where you just, well, I'm talking to engineers, so really. So this is where you actually, present a 2D representation of what you've done with detailed dimensions of each and every part. So, for example, the device I showed earlier, which is the noisemaker. So this is actually um, the 2D representation of it, of a part of it with the dimensions, as you can see here. So this, as you know, will help whoever is trying to actually do something with the model, let's say reproduce it or even 3D print it. This would help that person. So this is the third component of the SolidWorks, which is uh, the 2D presentation. So SolidWorks also supports a number of other features. It has CAM, that's computer aided manufacturing. It has that. It also has, like I said earlier, some level of animation. It allows some level of animation, but it is really restricted. You could only animate, let's say you can animate rotational motions and then let's say linear motions. It's not like Blender, for example, now where I can do a very, very complicated animation, but SolidWorks allows you to also simulate, do some level of basic simulation, which Blender also does simulation, but it's not as technical as what SolidWorks allows. So basically, the difference, I say one major difference I would say between Blender, for example, and SolidWorks is the fact that with Blender, you don't have to be so conscious of your dimension when modeling. It is really more for illustrations and then for will I say entertainment. That's basically where Blender comes in. You could also use it. You could model because all the software allow for they are really interconnected. You could do a model in Blender and then export it with specific file format into SolidWorks and keep on working with it and vice versa. But while working in Blender, it just allows you, it gives you that free room for creativity. Your limit is actually your skill level and then your imagination. You can do as much as you want in Blender. You could also Blender also can allow you, let's say if you model something like the model I showed previously of what looks like a boardroom. Now, this boardroom now was modeled. You see, the size of this boardroom you're saying is actually to specific dimension. Uh, it's actually to scale, so to say. But you see, I cannot really present this on an engineering paper. To do that in Blender, you'd have to have what we call add-ons. So you'd have to go an extra mile to actually get, other additional software that will allow you to actually now represent this in the 2D engineering paper format. So basically, Blender will just allow you to, do your model free of you having to worry about how accurate it is dimensionally. I just did this with dimensions because I already have a previous background when working with software that requires me to be conscious of my dimensions. So while if you go to SolidWorks, for example, now you cannot just model, it allows you to be creative also, but you need to actually be very conscious of what you're doing. Because take, for example, these two components, that's this and this. I had to make sure that, okay, the diameter of these two components is actually, there's just a gap, a tolerance of, let's say, 1.2 or so millimeters between them. So if for example the dimensions are not they are not coherent at all, let's say this is way smaller than what the dimension of this is, when you see the mates will actually not be accurate. So Um, so basically that's just a brief explanation of what this two software can do. Like I said earlier, in place of I just use Blender to explain because I'm more comfortable with it. But in place of Blender, there are actually a variety of software you could use, like I mentioned, Cinema 4D, 3D, XMass, and then Maya. But the difference is each and every one of those software I just mentioned now has a specific um it has a specific like function that it does well. For example, if you take Maya, for example, now Maya is more advantageous if you are doing sculpting. But if you take Cinema 4D, for example, it's good if you want to do animations. But you see, where Blender comes in is that it actually gives you the best of, well, let's say, both worlds. It allows you to do all those things without having to actually use any of those uh, software. Personally, my favorites. So the difference, that's just like that's the basic difference between SolidWorks and Blender. I think
Thank you. Thank
I'll
you.
stop here.
Thank you so much, Abdulhamid. Thank you very much. Can we have?
I don't know if
Can
there
you?
are any questions.
You're done, right?
Yes, I'm done.
Thank you so much. Can you maybe stop sharing your screen?
I think you have to override me. And
Uh, just click. You see this VUV meeting recording? Can you see it? VUV meeting recording. Up. Yes.
okay, yes.
Yes. Just stop. Just no, not that. Not that. Stop share. No.
Okay.
Yeah. Just click. Just
I'm not conversant with
yeah. It's okay. It's
this
okay. I
software.
understand. This is the first time you use it. It's okay. Yeah. Good.
Yes, that's
Yeah. I should mention that Abdulhamid is, a very great friend, highly talented. I'm not saying this because he's here, but he's very, very talented. And I actually he was to travel, but I stopped him from traveling and said, please come on, show us something that we can learn from. Thank you very, very much, Abdulhamid. Thank you so much. Thank you so much.
Thank you.
The next presenter is Haruna, is going to present on boogie mechanics. Haruna, please share your screen. Thank you very much.
Good afternoon, everyone. Can you hear me?
Good afternoon. We can hear you. We can hear you. We can hear you.
Okay, let me share my screen. Okay. Can you see my slide?
Yes.
We
We
can
can
see.
see. We can see.
Okay. Good afternoon, everyone. My name is Adamu Haruna, and today I'll be presenting on the boogie frame strength simulation using FEM and SFEM. Well, basically, for FE simulations, over the years we have been going towards autonomy and how to perform these simulations autonomously. Even people who aren't professionals in the field, they can still perform FE simulations without much difficulty. So today, what I'll be showing you is the procedures for performing boogie frame simulation. And the reason why I'm doing both FEM and SFEM is because the FEM, the standard FEM, has some limitations, which are poor accuracy and low convergence rate when using the linear triangular mesh or tetrahedral mesh. So one of the ways to improve on these limitations is to increase the order. Like instead of using the first order element, you can use second order. And another way is to use high quality mesh, which are quadrilateral or hexahedral elements, to increase the accuracy and efficiency. Another a proposed way of doing this is to use the smooth finite element method. The smooth finite element method, or SFEM, is a numerical technique for solving PDEs, partial differential equations, and it's an extension of the standard finite element method. This helps it to improve the accuracy and the solution time and the solution processes by adding an extra step. We call it the smoothing step, or the smoothing domain is introduced into the mesh. It's just an extra step. And for today, we'll be using the edge-based SFEM and the face-based SFEM to perform the static strength analysis of the bogey frame. Here are some available solvers in the SFEM code, because unlike softwares like Abacus and ANSYS, the SFEM uses in-house codes. So we have to perform some pre-processing and post-processing by ourselves. So the code only runs the simulation. It doesn't display results, or it doesn't, we can't manipulate our geometry or manipulate our mesh in the code. So some available solvers in the software are solid mechanics and structural mechanics, linear elastic statics, modal analysis, transient response, hyperelastics, and contact collisions. And here is my geometry, and the geometry was gotten from this bogey, which is the SFMZ33M1 bogey. It's mostly used in subways and metro. And one important aspect you are supposed to know is that when performing static analysis, we usually use a standard which specifies the loading and boundary conditions. So in this case, we use the CSU-HCAE 615 standard. It's a Chinese, it's an international standard. You can get it online. It specifies the load and the load and boundary conditions. This loading is what the bogey frame is supposed to withstand when in operation on the rail. So before we do this, I'm supposed to maybe give us a tutorial on how to do it. I'll just take it step by step. So first of all, I used ANSYS space claim. We have already heard about some CAD softwares from the first presenters. This is another one that came with ANSYS. Call it space claim. We use it to create and refine this geometry. One thing about performing FE simulation is that you have to be careful of edges, and you have to make sure that there are no gaps in your geometry. Like if you triple click it, you see everything is selected, which means that everything is one component. And since in this simulation, we're only using one material, which is steel, we have to make sure that there are no gaps. One way to check it is to come to repair. You can check for gaps, you see, no area found. You can check for missing faces, no area found. Just make sure you check your geometry. The next step is using hyper mesh. I think so. I'll just start the beginning so that we can get how it's done. So first of all, you import your geometry, which I showed earlier. You can, let me declare this, look for your geometry and import it here. Yes. After importing our geometry, we can either go straight to 3D because we need a volumetric mesh, or we can use 2D, which is the surface mesh, then later on use 3D. But since our geometry is okay, we can just create a component here. We can call it 3D. Then tetra mesh, then change it to trials here, because the others, these ones, apart from trials and out trials, the rest cannot be generated automatically. For example, if I use these quads and select my geometry, it will always give me an error because, these types of elements cannot be generated automatically. The only ones that can be generated automatically are the triangular or tetrahedral meshes. So after selecting tetrahedral, you can select all, or by collector, select our geometry, then mesh. one thing we should know is that the Abacus software can actually do all this meshing for us. But the reason why I'm using HyperMesh is because when performing the SFEM simulation, we need like an identical mesh so that we can compare our results for both of them. So we have our 3D mesh. Sorry, I forgot to tell us to specify our mesh size here. We have to pick a reasonable mesh size to mesh the geometry. Then I think we are done here. But what I like to do is, because I need to apply my loading and boundary conditions, I normally create entity sets. You can call it, for my boundary condition, you can call it UBC1. And just select the places. Like from the standard, we saw the areas where we can apply our boundary conditions. So we can just select this. Then you can create entity sets here. Normally, we need to select all these elements here, but since there's no time, I already have one which I did earlier. You can see all my boundary conditions, I created sets for them. Then the next step is to use Abacus and start from the beginning. So you just import, sorry. After you finish creating your entity sets, you need to export. You need to export this as server deck from HyperMesh. Then select where you save it. Because my mesh size is 50 millimeters, so I can just in this 50 millimeter one and save it as an IMP file. Then export. Then you can go to your Abacus and import the file. And import it as a model. Look for where you saved it. And change this to IMP. Sorry, that isn't the complete one. Import. So after importing, you can see our meshed geometry is here in Abacus. You can just come here and assign properties. Just assign section for the properties. The steps are already given here. If you don't have a geometry, you can start here by part and create your geometry by yourself. Or you can just come to properties. Since we already have our geometry and our mesh, you can just assign section, highlight everything, then press done. And click on homogeneous, continue. Since we are performing solid mechanics, click on general, assign your density. I think for steel is 7,800. And come to mechanical elasticity, elastic. The Young modulus for steel is 209. And poison is 0.3. So just press OK. As you can see, our material is assigned. Then come to assembly, create step by parts. Then come to step, initial, static, general, continue. Since there are many interactions, you can come straight to load. You can create a pressure load. And there's a shortcut here. You can just click by angle and select the whole surfaces. Yeah, and specify your matter. Yeah, specify this. I'm going to, since I've already done this here, I'm just going to come here. Yeah, I've already assigned my load and my boundary conditions. So you can just run it, job, come to job, create a job. And just yeah, you have to wait for the job to complete. So meanwhile, while this is running, let me show you how we do for our SFM. So unlike that of the FEM, you have to create some markers. And the way to do this is to create a face, like it's going to be like a 2D mesh around it. And the way to do it is to come to tools, faces, and select element 0 is our 3D mesh. So select it and find faces. Click on find faces. You see our faces will appear here. So from the faces, you can select the elements and name them marker 0, UBC11, UBC12, UBC. Your load, you can just rename them here. And you can come to organize. You can select your elements one after the other and can just move it to a new component. So let's see if our abacus is finished. Yeah, it's completed. You can view our results. As you can see, our omissus stress result is available. Our displacement magnitude in X, Y, and Z directions. You can see our results. So now we are done with the abacus FEM simulation. Let me show you how to do for the SFEM simulation. But first of all,
Haruna,
after getting your IMP file,
can you run over that really quickly?
Yeah. So after getting your IMP file, you need a CFG file to specify the type of SFEM you want to perform and specify static general, specify your material properties, and just after finishing all this, you can just click run and the simulation will start. You perform the simulation. Then after that, you get your results. Your results are given in VTU. This VTU can be viewed in ParaView, or you can save it in tech as VTQ, which can be viewed in TechPlot too. Yeah, let me just show you the results which you can get. Yeah, and just use TechPlot. Yeah, can view your results. Yes. Yeah. So we can view our results using TechPlot. So let me just keep all this. I've already performed the simulation. So here are our results. We can see that the FEM T10, because we can use the second order. The second order, we call them T10, and the first order, we call them T4. You can see that the one with the highest accuracy is the T10, followed by the ESFEM T4, then the FSFEM T4, then lastly, the FEM T4 give the least accuracy. So I think that is all. Thank you.
Does anyone in the audience want to interact with him on what he has presented? If you have questions or you want to say something? Anyone?
I have a question.
Please.
Yeah, regarding your results, you made mention that C10 has the best accuracy. How do you compare the accuracy? Do you have like maybe you perform experiment, then you get the actual results, then compare the result from the F10 and all this stuff, you compare it with
Yeah, I wanted to ask about that also because it was displacement against position. It had the highest displacement. Maybe you want to comment on that, Haruna.
Okay, Let me share. this again. So one of the ways we compare our results is to use the strain energy. So the strain energy gives the results for the whole body, which is the whole solid. And what I did was I performed 3 different simulations with 3 different types of mesh. So as you can see, the yellow, this yellow line here is the result for the Abacus FEM T10, and the blue line is the result for the Abacus FEM T4. So I performed 3 different simulations for each of them, and as you can see, one way to check for the accuracy is how different or how the results vary from each other. For the FEM T10, you can see that for the first, second, and third simulation, the results didn't really vary that much. So you know that it gave like a straight line, so the convergence is high. Unlike the FEM T4, the results for the first simulation, the second, and the third is like it varies largely. Then so that's how I got the limits from using the FEM T10 and the FEM T4. Then when performing the SFEM simulation, I also did for 3, using the same mesh for 3 different simulations, and you can see how the result when compared to the others, how they perform. I also did from this graph here, I did 10 different cases, which I applied different loading and boundary conditions based on the standard which was given for train working in operation. So I did, and in each of them, you can see that the FEM T10 performed gave the highest, how do I say it? In each of the simulations, the FEM T10 gave the highest result and the FEM T4 gave the lowest. Then you can see that the SFEM for ESFEM and FSFEM were in between. But the FSFEM were closer, they were much closer to the T10. But the T10 took more computational time compared to the others. And one thing we are trying to do is to make sure that our simulations don't take much computational efforts, whereby you can use just your laptop to perform these simulations. But for the FEM T10, I had to use a computer with more computational resources. So that's one way to compare it.
Thank you so much. Thank you so much, Haruna.
If you have other questions, please.
There are, but we cannot take them. So I also have to.
Hello.
Yeah, can you hear me, Haruna?
Just to add, can you hear me?
I can hear you, Frank. But sorry, we don't have much time, really.
Okay.
Yes, but you can go on. You can go on.
Just to add to the comparison, you can just have a result that you get from your what do they call it again? A reference result from your analytical analysis. So, but because this is a complex shape, so you cannot have an analytical result for it. But imagine it was just a simple cantilever beam. You can have an analytical result. Then your analytical results could become your reference by which you can compare the rest to. That's all.
I wanted to even say something like that. If you can do, I just imagine, I'm not sure, but if I imagine that if you can simplify this whole thing. So you have this boogie, this longitudinal connection, these two beams, I think you can call them beams.
Yeah.
This side beam will just be straight. So we have one straight side beam, another straight side beam, and then this longitudinal beam will also be straight. So you just have I don't know if you understand what I'm saying. Like you
Like
just
to
have
simplify the
yes,
geometry.
and then you can apply theoretical analysis on that. You know.
Yeah, but this
And
this is
also I wanted to ask, how do you explain? I don't know. Sorry, we don't have much time really. Yes, please, can you maybe just conclude on your thoughts? Thank you very much. Can you hear me?
Yeah, I can hear you.
Yes.
To conclude,
Yes.
this is actually a boogie frame. So the simplification we do, we have to be careful because this is like an already optimized shape. Do you understand? If we tamper with it too much, it will not be, the result we get will not be realistically applicable in um, in operation. You can't apply it in operation. So that's why we have to
What I
use
was saying,
the geometry.
what I was saying was if you had the simplified model that I was talking about,
Yeah.
it's not we are not comparing the simplified model with the real model. No, we want to test the Abacus FEMT for all these different models.
Yeah. Yeah.
On a
As
more
Frank
simplified
said,
one, so that we can
as Frank
verify
said,
by analytical.
yeah,
Yes.
we have already done that. Like we can use simple structures like the cantilever beam or disc to perform simple simulations. And the results
And
we
it's
got,
consistent with
sorry,
this
I did
one.
not put it here. The
Yeah,
results we got were
it's
similar.
consistent with this one. Okay.
Yeah,
okay.
it's consistent with this.
Then
That's what I'm saying.
That's it.
Yeah.
That's it. Really.
Yeah.
That's it. Yeah. Thank you. Thank you
All
very much. The next presenter is Frank. Frank, please. Can you please keep it short? Thank you very much, Frank. Are you there?
Yeah.
Please share your screen. Thank you.
Yeah, can we see my screen?
Yeah, we can see. We can see.
All right, so I will just give us a rundown on modal analysis. I actually do the same thing with Haruna, but just for the sake of our topic, just how to use Abacus to run modal analysis. That's what I'll be doing. So modal analysis, generally, we know, is used to get how our structures will react to vibrations. That's basically what it is. Aliyu has sent the link to this ANSYS tutorial in our group. I think one can actually go there and learn more from it. So modal analysis is a basic analysis that you would do if you want to be performing harmonic, random, and all this kind of dynamic analysis in general. So we'll be using Abacus to do that, and I'll be using a simple structure. So first off, we can create a simple cantilever beam just to show us how you can run modal analysis using Abacus. You can use other softwares like ANSYS. You can also use Hexagon. I'm quite sure it will be run on that. You can use SimScale. Just any CAE software you find yourself with. So we can create a part. So we're going to be running a 3D model. Approximate size, let's do 1 to 10. Then I create the model. So we can give it a dimension. Let's make here to be 1. And let's make here to be 0.5. So we can extrude it now. Let's make the depth to be 6. So if we have this beam, it's not yet a cantilever beam. We are done with the part. We can move on to the property. We'll make it, we are going to use aluminum. You don't have to create a set. So I select the model, then we'll name it a beam section. We'll continue, and a beam section will make it homogeneous. Then the material is aluminum. The density of aluminum, we know it to be 2,700 kilogram per meter cube. Then the elastic properties, Young modulus is going to be 71 exponential 9. That's the Young modulus. That's Newton per meter squared. Then Poisson ratio we know is 0.3. So we've created the property. Now we have to assign a section so that Abacus software, we have to create an instance so that the program itself can identify what you have done. So we don't need to make it dependent because it's just a simple cantilever beam. Then that is it. Then we'll create a step. That's how many, the kind of frequency you want. We are doing a modal analysis, so we're not going to be using static general. We'll move on to linear perturbation, select frequency, then choose the number of frequencies we want to get. So let's say the first 10 frequencies. Okay. Then from steps, we're going to move. We don't need interaction because we don't have other parts that we're going to be working with. Then we'll define the boundary condition. In modal analysis, you don't need loading. The loading is not required. So we'll just define our boundary condition. We'll take this into the initial. Let it start from initial. Then we'll choose where we want our boundary condition to be. So since we are trying to design a cantilever beam, we'll fix the end. Continue, we'll choose a fixed end. You see, all the directions are fixed to 0. So that is the loading. Then we define our mesh. So you can use seed part, you can use seed edges. So let us use seed part. So let's say we want in this edge, you know, the dimension we use is 0.5. I just want 2 meshes here. So we're going to divide it by 2. That's 0.25. So we can see. Then here now you can choose the type of mesh you want. You can use hexahedra, you can use tetrahedra, but let us use hexahedra. You can choose whether it is linear or quadratic. Quadratic gives you better results, but let us just use linear to save our computational effort. So now I can mesh the instance. So this is the mesh. Then we'll move to job. We'll create the job. Let's name it our tutorial. So yeah, you can increase if you have, let's say, multiple cores, you can increase the number of processors you are using or the computer memory you want it to use. So you can just go straight and submit it to use the default. So now we can submit the results, the model, and wait for like a minute because the mesh size I use is very coarse. All right, it's completed. You can actually monitor your results here and do a lot of monitoring and data optimization here. So now let's see our results, what it looks like. You can change this view. If I don't want to be seeing these meshes, I change it to feature edges. Then this is to see the undeformed shape, but now I want to see the deformed shape. So now this is what we have. So you can see that this is the first mode shape, mode 1. This is the second mode shape, third mode shape, up to the 10th one. So this just basically tells you that if you excite this beam in a frequency of 9.9, you are going to get this kind of deflection. These values, the magnitude, the modal analysis is not important. It is just the shape at which it's going to deform. That's what's important. What is actually going to determine the magnitude of displacement is the type of force or the amount of force that you applied. So basically, this is how you run a modal analysis. Is there any question?
Is there anyone from the audience who wants to ask him or interact on what he has presented? Anyone? Okay. Abdul Malik, are you there? Yes.
Yes, I'm here.
Please share your screen. Thank you very much.
Yeah. Can you see my screen?
Yes, we can see. Thank you.
All right. So, good day, everyone. I want to give a small talk concerning how to carry out simulation using ANSYS, or let me say how to conduct computational fluid dynamics. Okay, so I'm going to use softwares such as ANSYS, SpaceClaim, Rhinoceros, and so on. Okay, so the last time that we had the students conference, or let me say, the students talk, I talked about the various tools used in carrying out computational fluid dynamics or numerical simulation. Okay, so first we need to generate the model. Okay, what you want to do. In our own case, since we are going to be studying train aerodynamics, that means we want to study the flow around the train. Okay, so we need to create the train. Okay, so creating a train is really tedious. It's not a thing of just 1 day or 2 days or 3 days. So there are specialists for that, people who create train. Okay, we have one in the High Speed Research Center there. His own work is just to create different type of trains, depending on the specification that the lecturer or the researcher gave him. So the only the basic knowledge you need is to have a decent understanding of how to use some CAD tools, such as the SpaceClaim and the Rhinoceros. Okay, decent in the sense that you can modify your shape, you can make modification based on what you want to study. Okay, you can make sure that the model is correct, that when running the simulation you are not going to have any problem. So this is what I mean by decent knowledge of CAD tools. And after running this, making sure that your model is okay and your modification based on what you want to study is good, then you can now go to meshing. Okay, so when doing meshing, we have meshing softwares. In our case, I'm going to look at Fluent meshing package. So in Fluent, we can mesh and we can also conduct the simulation. Okay, because we know that in fluid dynamics, for people that are studying fluid, we have at least 2 discretization. I think it's also the same for people that study solid dynamics. You have to discretize the model, then you have to discretize the formulation. Okay, so when discretizing the model, this is known as meshing, trying to make small parts of these models so that you can compute it. You can compute this part, because you cannot compute the whole model. It's very big. Okay, so you have to discretize it, you have to cut it, you have to make it in a smaller shapes, smaller parts, so that you can compute it. You can compute each part and then you get a result for the total. Then for the discretization of the method, this is when now you do the simulation. Okay, you conduct the simulation, trying to compute these discretized model or mesh into trying to compute these discretized models using some formulas. Okay, some formulas. In this case, for people studying fluid dynamics, I think you must be familiar with the Reynolds average Navier-Stokes equation, or RANS, as we say. This is the basic. We have other formulations that are higher formulations because of improvement. With time, different researchers come with improvements. And after that, when finishing the simulation, then we are going to do post-processing. We process the results for us to have a visualized form of results for us to be able to interpret to the readers. Okay. Then for analysis, to analyze the result, because we can also have an output which are numbers in Excel form, then we can use them to also make other analysis. So in this case, we are going to use Excel, MATLAB, or Origin. Okay. So for the sorry. Can you see my screen? Hello?
Yes, the PowerPoint screen, right?
No, I just opened a
Maybe
software.
you need to reshare. Maybe you need to reshare. Okay, I can see. We can see now. We can see now.
Okay.
No, you have
This
to.
is
We can see the PowerPoints now. We are seeing the PowerPoint.
okay, just the PowerPoint. I opened
it just showed and then snapped back.
Oh, let me reshare them.
Yeah, you should have.
Okay. What about now?
It's good now. It's good. We can see.
Okay.
Space
So
claim.
this is space claim. In this, what we normally use this, or basically what we use this, you can use it to make your amends of the geometry. Okay. But what we basically do here is to ensure that the geometry is good. And then we also name some parts of the geometry. This is a train. Okay. So in this train, I have the head car, the middle car, and the tail car, for example, and other parts such as the bogie and the intercarriage gap structures. Okay. So to ensure that this geometry is correct, I'll go to repair, and then I will check for stitches. Okay. There are no stitches. Then check for gap, and also for missing faces. Okay. Ensure that every part is intact. There's no any problem. Okay. Also to group this train. Okay, because I want to study different parts, such as the bogie, the head, some part of the head, the intercarriage gap, and so on. So I'm going to group this train. Okay. So for here, I have already grouped it. So like I say, this is the bogie 1, the bogie 2, and so on. Okay. These are the various parts of the train, such as these parts. So here in this study, what I did is to apply a passive flow control device here, because normally in a train you won't see something like this. Okay, this structure here. So in this study, what I did is to apply this structure. Why I did this is because I want to reduce the aerodynamic drag of the train. Okay, so I put this structure, and then this is the modification I make here. So after grouping the train, then you can now save, and then after saving, then you can now move it to the meshing. So, but what I want, you must have to understand the various components you need before you mesh. Apart from the train, you also need a computational domain, okay? A computational domain and a body of inference. This is the body of inference, okay? So this is going to influence your mesh. So I have different boxes. These are boxes that are going to influence my mesh. So it simply means that the smaller the box, the smaller the mesh, okay? So if you can see here, I have different boxes. So this is small, then followed by this, and then this, then the bigger one, okay? So these are bodies that influence the sizes of the mesh. Then for the computational domain, this is like wind tunnel. I don't know if you know a wind tunnel. It's a place where you put the train. It's like a calculation environment. Okay, I want to determine the performance or the aerodynamic performance of this train or the flow structure around this train, okay, using this environment as my calculation environment. So it's just like that. Okay, so this is the computational domain. So what we are going to do is to put this train just like this into the computational domain. Okay, so you can see this is the train inside the computational domain, and also the BOI, which is body of inference. Okay, this is the BOI. Okay, so I just need to ship this because there was some modification I made. Okay, there's it. So this is a train surrounded by the computer, the body of influence, and then the inside, all of them are inside the computational domain. Okay, so after making sure that I have I've created my these three components, which is the computational domain, the body of inference, and the train modification that you need to do. Then I will now go to meshing. Okay, I will now save and then go to meshing. Okay, so here I'm going to use Fluent meshing. So here you open your Fluent and then you're going to select meshing. So because in Fluent we have solution, we have meshing, and we have icing. For this is for people that want to study the accretion of ice, or let me say accumulation of ice around a body. Okay, like for example for snowy areas. Okay, so you want to study how ice accumulates in a certain area and how you can now provide solution to this accumulation, okay, by using some passive device or active devices to either divert the position of this or the accumulation of this ice. So here we are going to do meshing. So after I select mesh, then I'm going to select the machine, the power of the machine I need to use, because here I'm going to use my own computer. My computer is not very strong, because for train, as we know, it's not like just a simple structure. I'm going to generate very large amount of mesh. So, and the most coarse mesh is maybe around millions of cells, maybe 10 million. That's the most coarse. So in some study, you see mesh of maybe 15 million, 20 million, even 50 million. Some, if you want to study using large eddy simulation, this is a method. You're going to use at least 80 million cells or 90 million cells, because you need smaller meshes to be able to compute the flow around the train. So I will now start. Okay. So I think it's okay. So I'll now import CAE, okay? CAD, sorry. So you now locate the folder where this geometry are. Okay. So this is the train. So I'll now import the train first. I think it's going to take some time because it's going to take some time to import. Most especially after let me just explain. So after I import, okay, I'm going to now create what they call scope size. Okay, this scope size is just like trying to create a surface mesh. Okay, because here we have volume mesh and surface mesh in fluid dynamics. I don't know about solid dynamics, but in fluid dynamics we have surface mesh and volume mesh. This one is assigned store. Okay, then I'll now import the domain. So here I'm going to use append. Append simply means that, okay, the importation of the current geometry shouldn't cause a loss of the previous one. Okay, so that's why I'm going to append. So I'm going to select this so that the former one is not going anywhere, it's going to stay. So I'll now import. Yeah. My computer is not that strong, so that's why I use the computer in the lab. So after importing these, I'm going to now import the body of inference. Okay, then I will create the scope size as I said earlier. So this scope size is trying to map or trying to create surface mesh on the train and the domain. Okay, so you are going to assign values to different parts of the train and different parts of the domain. Okay, these values are like mesh sizes. Okay, so after you finish importing inserting these values, then you write the values, and then you now write the the FD surface mesh here. As you can see, I don't use this option, not this option again. The CA here, the option to going to map on this surface mesh you created. Then after that, you're going to make some modifications, and then you now conduct the mesh. You carry out the volume mesh. And this volume mesh is going to take some time. Okay, it's going to take at least because now there's an improvement on the software, so it's going to take maybe 10 to 15 minutes. Okay, So this this class is not going to be enough for us to see the whole process of carrying out of simulation in this topic. So I'm just going to explain. Then anybody, if you have question or you have this is your area of research, you are doing computational fluid dynamics, you can meet me or you can meet Faisal or you can meet Hussein. I think these are the three people I know that are doing fluid dynamics. So you can meet them. They are very good in these softwares, and they are going to show you how to use them and how to go about getting the results and how to analyze the results and how to do a lot of things. Okay. So as you can see here, we are trying to even import the domain. It's still importing. So it simply means it's going to take time. But let me show you a simulation that is ongoing so that maybe you will. Okay. This is, can you see my screen?
Yes, we can see.
Okay, okay. So this is an ongoing simulation. So after you finish the meshing, I know it's difficult for you guys to understand what I just explained because most of you is not your field and you have not done it before. But as I said, if you want to do it, you can meet any of us to put you through. So this is an ongoing simulation. So after, like I said, it has a percentage. Yeah, this is on steady state simulation, so it's going to take a lot of time to finish. Like for these, I've started this simulation for almost, I think, 2 weeks. Yeah, 2 weeks. So I think it's going to take another maybe two weeks, yeah, to finish. Yeah. So this is a steady state simulation. For steady state simulation, it's not taking that time. Maybe in just 1 day, that's 24 hours, you are going to finish and get your results. Yeah. So I think let me just show some. Yeah, okay. It's going to take some time. Okay, now I think I can use this computer to show you what I was trying to explain initially about the dimension. So you import your geometry. Sorry.
Prof. I think we are going to maybe in the future invite you for a full blown
Okay.
into this. For now, I think you have around 5 minutes.
Okay. I think it's better because
Yeah.
it's
We'll
going
do
to
that.
take a
We'll
lot
do
of
that.
time.
We'll do that.
Yeah.
We'll do that.
Yeah.
We'll invite you
Because
for a
there's
full blown. You have the whole day.
yeah, okay.
Thank you so much.
Yeah.
Thank you.
Yeah, I think. Thank you. No problem. Yeah, you're welcome. All right. Thank you for listening to it. So
You
if
can
you
maybe you
have
can give us a
any
concluding
question,
thoughts,
okay.
or maybe if the audience have interaction points or questions or something like that, based on what you've
Yeah.
already presented, or maybe
So
if you want to show us more. Yeah, thank you.
just like as I said earlier, if after you finish, yeah, this is just a brief. So here I make a brief explanation of how to go about it. So here you design the train and the computational domain, you generate the mesh. Okay, you select the appropriate numerical method to carry out the simulation. Then you conduct mesh independent study. mesh independent study is to generate three mesh. You generate three mesh and you run the simulation, then you compare the results to see if there is too much difference in the result or not. If there is not too much difference, you carry the most less number of mesh, so the mesh with less number of cells. Okay, you carry it because you want to save time and energy. Okay, then after that you validate your results using experiments. Then you carry out what do you call it? You carry out the visualization. So I think basically this is it. And the point here actually is just for people that want to do it. Okay, you can meet me, okay, privately, or meet these people I said, and then they are going to show you, okay, how to go about it step by step. It's not a thing of 15 minutes or 20 minutes. So thank you for listening. If you have any question, you can ask.
From the
Hello.
audience, is there anyone? Yeah. Someone wants to ask? Someone speaking? No one. Prof,
Okay.
I wanted to ask very briefly.
Okay.
You made the computational domain.
Yeah.
There was the train was inside one, and then another one. Like,
Yes.
can you briefly explain that? Thank you.
Yes. So for the computational domain, okay, this is basically what you are going to see. This picture. Okay, even in papers, this is what you are going to see. Okay, but if we want to get a mesh, for example, let me show you. Yeah. So if we want to get a mesh like this, because you want to make sure that you study the mesh around the train, the mesh close to the train. The size of the mesh is very small, so that you can be able to compute the flow around the train, okay, near the train, correctly. So you are going to make sure that the mesh around the train is as very smaller, like this. Okay, we have fine mesh here, very close to the train, and then this mesh size decreases. I mean the mesh size increases. Okay, then you have a quasi mesh outside. Okay, so here is a computational I say body of inference. Okay. Oh, okay. Yeah. So here, this can you see?
Yes, we can see.
Okay. So just as I said, so you want to make sure that the mesh close to the train body, okay, close to the surface of the train is small. Okay. That's why you are putting these things that you are seeing. They are called body of inference. Okay. These are the okay. So here you are going to generate a smaller mesh using the smaller box here, then followed by this one, and then this one. Okay. So the mesh size is going to be increasing with the size of the mesh and then size of the box. I don't know if you understand.
Yes, I do. Thank you so much.
Okay,
Thank you
so
very much.
sure.
Thank you. Are there any other, even though we are very constrained and I'd like to round.
Hmm.
Any other questions from the audience? If there are none, thank you very much for this wonderful session. And I really, really hope, because I really enjoyed it. Believe me, I enjoyed this session. And I hope that the audience, everyone who has come here to support us in this venture has also
So again,
enjoys
I
this.
want to urge
Yes,
with the
yes.
audience. You guys should try and have people that are studying fluid dynamics. Okay, because I noticed that people studying fluid dynamics are not much. Most of the people we are having here are people studying solid dynamics, and then solid parts of the mechanical engineering, and then no people studying like the fluid parts. So I think it's good if you have people that people that just come recently. I think it's good to also think of that side, because we have a lot of interesting research areas also in these parts. Okay, we have sound. We have, apart from that, we have sound. We have other interesting parts that you can explore. Okay, so thank you very much.
Thank you very much. Thank you very much, Prof, for your counsel. And I thank everyone who has come here to participate in this wonderful, session. And I hope that it is as interesting as it is it is interesting for you as it is as it has been for me. And as you know, this is the first session. I hope that by next week, most probably next week or upper week, as the case may be, and this will be communicated effectively in the group, that we're going to have the second and last session for this Hexagon CAE. And I hope that you've learned something and you've been inspired by some of this presentation. Thank you very much. Thank you very much. Thank you very much. And this is the end of this session. Thank you.